So let's talk about curves and surfaces. So a curve is just what we get when we take a continuous mapping of R, or some subinterval of R, and we map it into some higher dimensional space, R2 or R3. And a surface is what we get when we take R2, or some subset of it, and map it into some higher dimensional space, like R3 or R4 or something like that. So let's go over a couple of basic examples and then some exotic variations we can get from them. So we're going to look at the circle and the straight line path from one point to another. So the circle is typically parameterized just cosine of t sine t, and we only need t to go from 0 to 2 pi. We don't need the entire real line for this one. That'll be enough for us to get the unit circle traced out in a counterclockwise direction exactly once. And if we do something like change it by, say, let's multiply it by 2 out in front here. So that would be the same thing as putting a 2 in front of the cosine and a 2 in front of the sine. Then we would get a circle with twice the radius, right? So pretend that those are actually concentric circles here. Maybe I can adjust this a little bit so it doesn't look quite so lousy. There we go. And then we can start getting like fancy with it. So we could take, let's take again cosine t sine t from 0 to 2 pi, but now I'll change the radius by t. So the radius starts off at 0 and ends at 2 pi. And so now it's going to actually give me a spiral ending with a radius of 2 pi by the time I'm done. And I could do other things, like I could look at, I could take cosine of t sine t, and I could add some other vector to it, like 3, 2. So that would be the same as 3 plus cosine 2 plus sine. And that would have the effect of, let's say, 1, 2, 3, 1, 2, moving the circle so that it's now centered around the point 3, 2. So then it would go something like that. And we could go even further with this. Suppose we had cosine of t sine t t. And then we're still going from 0 to 2 pi, but now we're in 3 dimensions. And so let's see. So if I fixed the third coordinate here to be equal to 0, it would trace out this path in the xy plane. But since it's not fixed equal to 0, it's going to be increasing over time. So it's actually going to trace out this path here. And if I've drawn that correctly, then the height that we end up with at the end should be 2 pi. So we get a helix, a vertical helix, kind of spiraling upward around the z-axis. Okay, so there's fun and games we can play with the circle. Now let's look at our other sort of standard, basic, need-to-know-it example, the straight line path. So actually, let me back up. So suppose we have 2 points, A and B. So here's A and here's B. So these are points in some R2 or R3 or whatever. I didn't draw the axes just so that I don't have to like specify. Then I'm going to take f of t to be 1 minus ta plus tb. Now as t varies from 0 to 1, this is going to give me the straight line path from A to B. So notice if I set t equal to 0, then this part's gone, and this part's gone, and it just evaluates to A. So f of 0 is A. And if I set t equal to 1, then this part's 0, so that whole thing drops out, and this part here just evaluates to B. So then this is f of 1. And then if we take some value in between, like say t equals 1/2, then that's going to be 1/2 a plus 1/2 b, which you can rewrite as a plus b over 2, and you recognize that as the midpoint, so that's halfway in between. So you get the picture here. So this gives you a straight line path from a to b. And it's also worth doing something with this formula here where we rewrite it in a slightly different way. So if I multiply out the 1 minus t, then this looks like, and collect the t terms together, I can rewrite that formula like this. And this is important because what you see is that this vector here, b minus a, that's the vector from a to b. So the one that points from a toward b. And so let me just redraw the picture. So here's a, and here's b over here. Then the vector, and let's give some coordinate axes now just to ground this thing. So the vector from a to b is this one right here. So this one is AB, or B minus A. And so the formula is telling you here that you start at A when t is equal to 0, and this term is gone, and then you move in the direction that would take you toward B. And the reason why I want to make a little bit of a fuss about this is because people often have a tendency to write down something like this. Let's start at A and then go in the direction of B. And that is not what you mean, because this vector here, that's B. So if you start at A and you move in the direction of B, you actually end up going parallel to B, and you never get to B. You don't get within this distance of B. Okay, so the straight line path from one point to another. Okay, so that's some examples of curves that are good to know and love. I'm going to talk a little bit about surfaces, even though we actually won't really get to surfaces until chapter 17, and even then only briefly. So you can just kind of sit back and enjoy the ride. There's nothing here you have to remember really or memorize. This is just an example of where this stuff goes. So let's take our variables to be phi and theta because they're most commonly used for this. And we'll take them to, our output to be sine phi, cosine theta, sine phi, sine theta, and cosine phi. So this is a map from R2 to R3. And we're going to take phi between 0 and pi. And we'll take theta between 0 and 2 pi. And so let's see. So we're going to be mapping from this little phi theta rectangle that looks like this. And we map it into R3. And what does it look like? Well, if we look at these horizontal strips right here, and we look at what is the image of those under this mapping here, each one of those corresponds to a fixed value of theta. So for example, for theta equals 0, the middle term drops out, and so we have sine phi in the first coordinate and cosine phi in the last coordinate. Oh, so that you just recognize is a circle. And so that would be this circle right here in the xz plane. So this corresponds to when theta is equal to 0. And then as theta increases, you get, and this gets a little bit tricky to draw, circles that look like this, and like this, and like this, all the way out here until you get to the one that passes through the yz plane, where theta is equal to pi over 2. And then you keep on going around and around until you get to theta equals pi, and continuing and so forth. And sure enough, you get a sphere. So this is a parametrization of the unit sphere, and that will actually be useful a little bit when we look at parametrizing integrals in the latter part of chapter 16. For now, don't worry about it. It's just a picture. Here's another example of a surface. This one's kind of cute. So it's going to be r plus little r cosine phi, and then we take that whole thing and multiply it by cosine theta. That's our first coordinate, or first component function. And then we have r plus r cosine phi, and then times sine theta this time. And then for the last one, we just have little r sine phi. What does this do for us? Well, let's see. We can figure this out by looking at when theta is equal to 0 again, and then generalizing. So when theta is equal to 0, this is r plus little r cosine phi, r, and then 0, sorry. And then r sine phi. And that looks like r0, big R0, plus little r cosine phi sine phi. Okay, so now we can break this down and say, oh, okay, so this here is going to be a small circle, right? That's the parametrization of a circle. And then it's been shifted in the x direction out on the positive x-axis. So if I draw what this looks like, it's going to be this circle out here, and so this is supposed to be in the xz plane, and it's out here, and it's at distance r, and then the radius of this little circle here is little r. And now what happens is, as theta changes, the circle moves. So now we're at capital R on the positive y-axis, and it just keeps on moving around, and we end up sweeping out a donut. So it gives us a torus. All right, so there's a fun one. And then one last one, just to tie a couple of things together. Suppose that A of S is some curve, and B of S is some other curve. So maybe, let's see, so maybe A of S looks like this, and so that's A of S. And so I guess we're in R3 here. And then maybe B of S looks like this. Let me move that label, it's kind of ended up in the way. Right? And then I'm going to define f of st to be, and now watch this, I'm going to go 1 minus ta plus tb. And so you know what that is. That's going to give you the straight line path between A and B, but now A and B are curves. So we end up getting a surface we get this what's called a ruled surface, because it's made up of all these little straight lines passing between those two. Okay, so those are the basic examples for curves later on and surfaces. Later on in chapter 17, we will look at vector fields. All of chapter 17 is about functions that go from R2 to R2, or from R3 to R3. The main point just being that the domain and codomain both have the same dimension. So it's from the same Rn to the same Rn. But we're not going to get to that for a long time. Next, what we're going to be looking at through most of chapter 15 and 16 is R-valued functions. So things that look like a function from R2 to R, or R3 to R. Sometimes these are called scalar valued functions.